Assalamualaikum and hi everyone. Today our group will talk about the role of Higgs boson. So first of all, let me introduce to you a fascinating concept from the world of physics, the Higgs boson. The Higgs boson is a particle that serves as the carrier particle or boson of the Higgs field. This field permeates all of space and plays a fundamental role in our universe by endowing all elementary subatomic particles with mass through its interaction with them. Though it may seem like an abstract concept, the Higgs boson reminds us of the intricate connection that define our world. This interaction shapes everything from the smallest particle to the largest structure in our universe. And also, they inspire us to consider how even the smallest action can have profound impacts.
I will continue with the discovery of Higgs particle. The origin of the Higgs boson began on 1964 with Peter Higgs and several other physicists proposed a mechanism to explain how particles acquire mass. This became known as Higgs mechanism, which predicted the existence of Higgs boson. For many years, the Higgs boson was just a theoretical idea without any experimental proof. In 2008, the Large Hadron Collider (LHC) was completed at CERN, becoming the world's most powerful particle accelerator. It was designed to investigate the energy level that necessary to discover the Higgs boson. On July 4, 2012, CERN announced the discovery of particles that matched the Higgs boson. This finding came from data collected from proton-proton collision. Two main experiments, ATLAS and CMS, reported similar results, identifying a new particle with a mass of about 125 giga-electron-volt per light speed squared. In 2013, Peter Higgs and Francis Englert were awarded with the Nobel Prize in Physics for their contribution to the understanding of the mechanism that gives mass to elementary particles. Research at the LHC and other facilities is ongoing until now to further investigate the properties of Higgs boson, its role in the universe, and the possible link to new physics beyond the standard model.
Next, we continue with Higgs boson properties. Firstly, the mass of Higgs boson is 125 giga-electron-volts. The mass of Higgs is critical because it allows the particle to interact with others in the Higgs field, giving them mass through the Higgs mechanism. The Higgs boson has electric charge of 0. This neutrality is consistent with its role as a scalar boson and ensures that it does not interact electromagnetically. The Higgs boson is a unit that has a spin of 0, making it a scalar particle. This is distinct from the other particles in the standard model, such as fermions, which have spin of half, and boson, which have a spin of 1. Its spin 0 nature was a key prediction that helped confirm its discovery.
The next property is the standard model predicts the existence of self-coupling, which regulates the strength of the interaction of the Higgs boson with other Higgs boson. The self-coupling plays a pivotal role in shaping the potential energy of Higgs bosons and is ultimately responsible for giving mass to elementary particles. While physicists have been diligently investigating the properties of the Higgs bosons for over a decade, measurements of the Higgs self-coupling are more challenging. The decay modes of the Higgs boson refer to the various particles it can transform into after being produced. These decay modes depends on the Higgs boson's mass and interaction with other particles as predicted by the standard model. For example, the decay of the Higgs boson with bottom quark-antiquark pair. From this, we got the branching ratio approximately 58%. This is the most common decay mode as the Higgs interacts strongly with heavy particles. The Higgs boson is an incredibly short-lived particle with a lifetime of about 10 power of negative 22 seconds. After it produced, it decays almost instantly into other particles like bottom quarks, W or Z bosons, or photons. The study of Higgs boson continues as scientists aim to uncover more about its role in the universe and whether it might offer insight into physics beyond the standard model.
Next, I will talk about the roles of Higgs boson. They are mass generation, that providing mass to fundamental particles, connecting the microscopic and the cosmic, electroweak symmetry breaking, and technology advance. Facilitate mass generation for elementary particles via the Higgs field. The Higgs boson is linked to the Higgs field, which gives particles their mass. W and Z bosons gain mass through the Higgs field, explaining the weak forces short range. Fermions consist of quarks and leptons, gain mass proportional to their interaction strength with the Higgs field. Next one, connecting to the microscopic and the cosmic. The Higgs field might influence the universe evaluation, contributes to understanding the stability of the universe vacuum, essential for forming atomic structures, stars, and life itself. Without it, all fundamental particles would move at the speed of light, preventing the formation of matter. In summary, the Higgs boson is an associated field of vital in cosmology for explaining fundamental aspects such as the flatness and uniformity of the universe, structure formation, the transition to a hot Big Bang, baryogenesis, and potential dark matter production. These contributions highlight the importance of the Higgs boson beyond particle physics, extended into our understanding of cosmic evaluation and structure.
Next, electroweak symmetry breaking. In the early moments of the universe, all particles were massless, and the electromagnetic and weak forces were unified under the electroweak force. This perfect symmetry made particles indistinguishable, but as the universe cooled, a hidden player came into action, the Higgs field. The field spread across the universe and broke the electroweak symmetry, causing particles to interact with it in unique ways. For example, the W and Z bosons, the carriers of the weak force, interacted strongly with the Higgs field, gaining significant mass. In contrast, the photon, which carries the electromagnetic force, didn't interact at all and remained massless. The difference explains why the weak force is short range, while electromagnetism operates over vast distances. This process, known as spontaneous symmetry breaking, transformed the universe into the structured and complex cosmos we see today. It's a cornerstone of the standard model and explains why particles have the masses they do. Lastly, technological advancements. The discovery of the Higgs boson wasn't just a theoretical breakthrough, it was a triumph of technology. The Large Hadron Collider, or LHC, at CERN was instrumental in this achievement. The LHC is the world's largest and most powerful particle accelerator with a circumference of 27 kilometers. Inside, protons are accelerated to near light speeds and collided head-on. These collisions recreate conditions similar to the first moments after the Big Bang, providing the perfect environment to study fundamental particles. These innovations not only helped discover the Higgs, but also found applications far beyond physics. Particle physics technologies have impacted many fields. For instance, detectors developed for the LHC have improved medical imaging techniques such as PET scans used in cancer diagnosis. Radiation therapy for tumors also benefits from precise particle interaction measurements developed for physics experiments. And the data processing techniques created for particle analysis are now widely used in industries like finance, artificial intelligence, and big data analytics. In conclusion, the discovery of the Higgs boson was a monumental achievement in particle physics. This particle connects physics with cosmology, helping us understand the forces that shape the universe. The Higgs boson is more than a particle. It's a key to unlocking the universe's greatest secrets. And as we continue to explore, its story is far from over. Thank you for joining us on this journey into the heart of particle physics.